Hello, good afternoon. Yeah, for those of you who were at BobConf last year, you may remember that I gave a talk about general functional programming in Swift because yeah, I thought there's a need to tell people about it in this community. And today what I want to do is kind of a deep dive into one of the topics which I kind of touched on there. But before I do that let me say a few things about Swift. So who actually has used Swift? Okay, a few hands. And that kind of reinforces my belief why I've given the talk last year and I'm giving this talk this year. A lot of people think Swift are this Apple thing, right? I don't want to write apps for iPhone, so it's irrelevant for me. But that's an outdated impression. So Swift is actually a cross-platform, open source language which is developed by an open source community. Even the GitHub repos are not under Apple's organization anymore. It's a very community-driven project where a lot of people who contribute are paid by Apple, but I mean, this like a lot of people who contribute to Haskell are paid by IAG or something. And it's a multi-paradigm language, so it kind of combines features from functional programming and object-oriented languages. But out of the there are more languages in this family, right? Scala, Kotlin, and so on. And I think it's interesting to see, so what's the distinguishing factor of Swift? And I think there are two. So one is Swift really has the goal of being very performant. And that when Chris Lesnar at WWDC 11 years ago announced it, he already said, I envision this language to be a language for systems programming, low-level programming, up to complex applications, right? We want to do the whole thing, which is quite unusual these days. Usually languages focus on one or the other, high level or low level. And the other thing that distinguishes it, and that's why I'm here, it has a very strong functional core. Out of all these hybrid programming, multi-paradigm programming languages, I think, and that's the case I tried to make last year, so I won't go into this any further, is it's the language which is best suited to functional programming. And the community which is really taking functional programming the most serious out of those communities. But there's always a but, right? The one annoying thing is Apple marketing. Because, you know, Haskell marketing is shit, right? We use fancy, complicated names for everything. And that kind of sometimes increases the learning curve quite a bit. So now Apple does the extreme opposite. I guess nobody's surprised about that. And they try to make it kind of sound simple, fun. So they rename everything. And then for us, it's hard to notice, oh, they're actually talking about functional programming because they won't use that word. And also for the people in the Swift community, it's hard to see, well, there are actually other people out there who talk about similar things in other languages. Now, the second one is addressed by, there are actually conferences about Swift which have a very strong focus on functional programming and say that using those words. So that kind of is a little bit addressed. But the other direction, I thought I have to come here and tell you about it. So if I ask you, tell me one, your favorite, whatever, defining characteristic of functional programming, what would you say? Don't tell me it's using functions. I mean, everybody in the world is using functions. So that
Declarative?
Declarative, yeah, but what does that mean?
That you define, it's a definitions, right?
Yeah, but every programming language has
No
different.
instructions.
Higher order functions, I think, is a great one. The only problem is these days every language, even Java, has closure, so that doesn't work anymore. It used to work. Peter? Referential transparency. Yeah, so kind of something about reasoning. That's very good. Yeah.
Lots and lots of like allocations.
Many allocations. Yes. That's so. You're the cheeky one. I noticed that. So let me pick one which, I mean, Peter is going in the right direction. I think immutable data structures, right? I mean, that you have data structures and you have algebraic data structures, so complex data structures, and they're immutable. And that makes it formally or informally easier to reason about them. I think that's a core feature. So now, I told you about renaming. Apple calls this value semantics, and that's kind of the core of what I want to talk about. And in fact, this value semantics is paired in Swift with the opposite, which is reference semantics. So what do I mean when I talk about value reference semantics? Well, simply, if I've got a vector composed out of two components, right, that's bound to variable v1, and then I define a second variable v2, and I say, well, that's the same as v1, then what everybody has in their mind is like it's the same thing in there, but if I somehow update the first component of the second vector, then this one stays the same, right? This is like our intuition. It's immutable. This thing didn't change only because we did something to the other thing. Whereas with reference semantics, we've got a, reference to the actual data. And when we've got this assignment or binding, whatever, then really we only copy a pointer. And then obviously, when we update, we change everything. And yeah, that might be surprising. And the exact same thing goes for parameter parsing, right? I parse something to a function, and then if I change that something in the function, then the caller is affected or not, depending on reference or value semantics. Okay, so very simple concept, but Swift kind of expresses that very clearly by introducing the notion of value types for value semantics and reference types for reference semantics. And so we actually have two ways of defining value types, namely by defining a structure. A structure is Apple speak for product. And by defining enums, which is Apple speak for sums. And now you could think, you would be kind of, I can't fault you if you think, yeah, enum is just a list of different alternatives like labels. Yeah, but you underestimate Apple. Enum in Swift is actually fully fledged sum type with arguments, and you can define recursive lists in that way. Like in Haskell. And if you want to know the details, well, there's a video of my talk from last year. But they call it enum, because if they would say algebraic data type, people would run away. But enum, nobody runs away. So much for the renaming. And then for reference types, we have class definitions, and we have actor definitions. And the actors are basically like classes, only they are particular isolation properties in the context of concurrent execution. And yeah, I won't talk more about actors. It's a nice topic in itself, maybe next year. So the nice thing here is really, if I want to know for a value, or if I want to know for a variable in my program, is this thing inside, is it going to go by value or reference semantics? I just have to look at the type, and at the declaration of the type, a null node. Very kind of clear definition. Okay, so that if you look at that in code in Swift, well, we can have two definitions: a vector as a struct, a vector as a class, and then when we create one of these structs and we do what we had in the previous example, then obviously the initial vector has the old value, whereas if we do the same thing with a class, then both of them change because we only copied a reference. So now a bit more subtle is, I mean, there are lots of vars here. Well, that's not the whole story in Swift, because I mentioned there's a functional core in there, so I could write let. And what that means, I'm telling the compiler, the variables I'm defining, they're immutable. Now, previously they weren't immutable, obviously, because otherwise I couldn't have done that. Well, I can't do that in a second. But even if I make them let bound, I can still do that. Why? Because this means I make the reference immutable. So I wouldn't be able to update it with a different reference. But the referred to thing, well, that's a different story. On the other hand, here, it's different. Here, I can say v1, which I actually don't want to change, is immutable. But here I get a copy of v1, and if I want this assignment to succeed, this has to stay a variable binding. If I turn this into let, the compiler will slap me on the fingers. Okay, so you see the Swift compiler is quite picky about mutability, controlling mutability, and statically inferring what is mutable, what not, and what you can apply to what. Okay, so that's the basics. Where it starts to get interesting when we look at what I call bulk value types. So what's a bulk value type? A string, for example. Now, if you look at the documentation for strings in Swift, then it says struct. I told you, if you want to know for some variable whether the thing inside goes by value or reference semantics, you look at the type and then look at the declaration, and is it a struct enum, value type? Is it class actor, reference type? So this must be value semantics. This must obey value semantics, right? Otherwise, I would have lied to you, which I would never do. Okay, so let's have a string. Well, it's let bound. So if I try to append, plus equals is append something to the string, then the compiler is unhappy with me. Rightly so, because I said this thing is immutable, so obviously I can't add something to it. Now, if you have just plus, that's append, that's like plus plus in Haskell. That's a different matter, but then you get a new string. Here we are talking about in-place append. But I can have a second string, hello world, which I say is the same as hello, but it's a var, and then I can do this, and the compiler doesn't mind. Okay, so we have mutable strings, we have immutable strings, but it's always a struct. Now, when I print the original one, no surprise, it's like with the vector, then the original string, of course, didn't change, only because I changed that one. Value semantics. So they didn't lie here. All right, so good. So far, so good. Now, let me say something about strings in Haskell, which you all already know, right? We have strings, which is nice and easy. This is always in my first year lectures. I would always explain strings like it's a list of characters. Very nice, easy for students to understand, but it's completely useless most of the time. So we also have byte strings, which is kind of like an array with characters in it. Yeah, but it's 2025. by now, and I mean all strings are Unicode, so this really doesn't cut it either. So we have text too, and it understands Unicode. So yeah, slowly it's getting a little bit annoying, and this is just the immutable versions of things because, well, maybe I mean I forgot your name. Micha, I told you that I wrote an IDE for Haskell. So in an IDE, you need a buffer, a text buffer, and there are people changing individual characters quickly, and many of them. And then all of this is totally useless. Well, maybe you use an M vector wrapped into a state monad or something like that. So strings is a little bit of a mess. The nice thing about strings in Swift, that one structure type does all of this. That's not bad, I would say. Okay, I'm biased. Okay, so let's take a different one, because strings, there are many programming languages have string special case. So in Java, strings are also immutable, and it's a mess, but it's a special case. But let's look at arrays. So, also struct. That's even more surprising. So I can do something similar again. I define an array variable with stuff in it, and I can kind of apply a map function, and then I get a new array. So what you would expect of a functional programming language, basically. I can project individual elements out of that, and I could try to assign something to it, but then the compiler is unhappy again, because I wrote let. Okay, so I can change that to var, and then I get a mutable array. Right? It's still the same type. And well, then you may think, how is this working out with this value semantics thing? Well, let's define a function. It's a bit involved. So we pass it an array. This is shorthand notation for arrays. An array of integers. And then, well, I'll get to this, and then apply a shuffle function. Shuffle is one of the library functions. It just messes up the elements, I mean, different order. And then we print it. Now, here we call this shuffle function, print shuffle function, with our variable. So we could update it. I mean, it would work here because it's mutable. We pass this into this function. But it won't change. This has still the exact same contents plus the update. So it has this value. It didn't change. In fact, I've got this line in here where I just kind of say, OK, give it a new name. But this is not just giving a new name, because everything I pass in value types has value semantics. So this is kind of like as it was let bound. And in order to apply shuffle without the compiler telling me off, I had to make it a var here. So obviously there's more going on behind the scenes. And the nice thing, value semantics is preserved. Whew. My semantic heart kind of is very happy about that. Okay, last data structure, dictionaries. Dictionaries are kind of hash table. So you have, it's parametric over key and a value type. A key type has to be hashable. This is Swift notation for protocols. And protocols, they call protocols because they thought, I guess, type class sounds too scary. So this is same as if in Haskell you had written hash table key. So it means key is an instance of the hash table class. OK, so that makes sense. And it also is a struct. So you can do the same as with arrays. You can have an immutable, mutable versions, and so on. All right. The nice thing is it's not just that they are library data types like that, but you can make your own. Quite easily, actually. So you might say, OK, cool. If I just brutally copy everything everywhere, surely I can gain the semantics. But, well, then I will use a lot of memory, and it will be slow, and people will cry. And didn't I say Swift is kind of a performance-oriented language? So that's weird. Well, just as a, I'm not giving you benchmarks here, but as a kind of case in point, this is the new app I'm working at. It's a new IDE for functional languages, so you can do Haskell. And it's implemented in Swift, that's why I'm mentioning it. And the files and buffers for the editor are just strings. No weird stuff going on. Well, there's weird stuff going on, actually, but OK. So this is actually quite flexible. So now let's summarize what we want out of this bulk value type. So bulk collections, for example, but with value semantics. Well, we want value semantics, obviously. And we want to somehow have it performant. And that means we shouldn't copy too much. So how can we achieve that? Well, using cows. And that's a technique which is used in operating systems a lot. So how can we use it here? Well, let's look at two extreme cases. If I'm taking a simple root and I'm just copying like crazy, which with these small vectors is something you can do, but certainly not with arrays or dictionaries, then every time I introduce a new name, I copy the data. And if I do that a few times, then I copy and copy and copy. And now memory is full, and I've got a problem. So the other extreme case is to say, OK, I box this data, right? I put it on the heap and in the box form, and then I just pass references around. But then my semantics goes out of the window, because if in between somewhere I call one of these mutating functions, and this v8 is var-bound, not let-bound, then everything is wrong. So this is very fast, but also very bad. So both is bad. So what we actually want is this. We want to use this pointer representation, but we want to be smart. And we want to catch the places where we want to change something, and then just before we change it, we copy. OK. So this is called copy on write. And your operating system, for example, is using it to manage memory pages in order to minimize copying processes, memory pages of entire processes all the time, or share libraries, for that matter. So how does copy and write work? Well, we put stuff into a boxed representation, and then we just use pointers to that box as by default. But when we notice something is about to get mutated, we copy it, but only if there's more than one pointer. Because if there's only one pointer and we use the structure only linearly, we can immediately reuse the storage, and there's no point in copying. Right? So that's what we want. But how can we achieve that? So in Swift, specifically, well, there are actually two cases. So case one is where where the payload is of fixed size. So it's, for example, a struct, but it's a struct with a lot of properties, or some properties which are quite big. And then what we want to do, and I'll explain how we do that and what that exactly means in a second, we want to intercept the property setters somehow. It says intercept property setters. Yeah, I'm sorry, I shouldn't have put anything below here on the slide. the second case is dynamically sized structures. Yeah, examples I gave you: string, array, dictionaries, sets, whatever. Well, these are collection types. And there we want to intercept mutating functions somehow, which in most programming languages you can forget. But I already told you Swift is really, really, really picking about tracking mutability. So maybe we've got a chance. Let's start with number one, fixed-sized bulk value types. The example I mentioned, so you have a struct. It has a few properties, and maybe some of them are quite big. This happens a lot in typical Swift programs, especially in typical Swift programs you write in the way Apple recommends you to do, because Apple, in its we promote functional programming, but we don't tell anybody about it. Tell people when you define the model data structures for your apps, try to use only structs and enums, and only use classes as a last resort. Why? Because they want them to use immutable data structures, value types. And so you get a lot of those in your apps. And then the question is, how can we make that as efficient as possible? So maybe using copy on write. So in order to do that, remember step one for copy on write was box your data. So we turn the struct into a class, and then we copy all the properties in there into the class. And we write a function, copy, which makes a new box with the same information. So it makes a copy of the box. But you have to explicitly call it. It doesn't happen automatically. All right. So now that we've got our box, we have to define the actual struct. Now the struct doesn't contain the data anymore because we've put the data in the box. So we have to put a reference to the data in the struct. So we got the box as the only property in the struct itself. But what do we do about these properties? Now the struct doesn't have any properties anymore, right? So let's take the first one. Now usually properties introduce storage, but Swift has something which is called computed properties. And computed properties look like properties, use them like properties, but they're actually doing computation. And they can have getters, which read something out of this property. And what we do in the computed property, we just forward that read to the box and return the result of whatever the box returns for this property. Now with the setter, we can kind of do the same. We change the property in the box, and new value is just, this is part of the Swift language in a setter. The new value is called new value. But that's wrong, because that always changes the box. There's never any copying, and we will be very sad. So we have to, what we said on the slide of how do we implement copy and write, we have to check whether there's more than one pointer to the box. And this is where the magic comes in. We have this weird function, I'll say more about this in a moment, and which we apply to the box. And if is known uniquely referenced, Apple likes long names for functions and about everything. Did you notice? If that's not true, then there are multiple pointers to this box. And then we need to copy it. And luckily, we defined this copy function, which everybody past the second row can't read, but here's the copy function. We have this copy function, which we give the old box, make a copy of it, and put in our box property. So now we've made a copy, and now we can update the copy. Everything is good. Value semantics survives. Okay, so what about this weird function? Well, it's got a weird type too, and I won't explain everything about the weird type, but you may wonder, how does it know? Well, what you maybe didn't know is Swift uses reference counting. Now you may say, reference counting for function language, who would do something like that? Well, I'll come back to this later. Before we talk about that, well, an observation. We started out with one property, and now we have all this gunk in our program, and that's just for one property, and the whole point here was we did this because it's a big struct and there's a lot of properties. Do you hate boilerplate too? Yeah, me too. So this seems like, and it's bad boilerplate. You forget the negation before the is uniquely blah, 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 and all hell breaks loose. So luckily, in one of the more recent versions of Swift, macros were introduced. And macros in Swift are kind of like template Haskell, but then a bit saner, also a bit more restricted, and it perfectly works with cross-compilation. Imagine. Anybody try to get GLC to cross-compile out? No. Okay, then try it. Then you know why I'm saying this about cross-compilation. Well, and using those macros, this guy, Rick van Voorden, has implemented a library called Swift Cowbox, and it allows you to take normal struct, put a few annotations in it, and it generates all this boilerplate for you. Win-win. And at Swift Connection in Paris last year, he gave a talk about it. So if you're interested, watch the talk. All right, let's get to the second one. Dynamically sized arrays, stuff like that. Well, let's actually look at arrays. So array is a struct, and it's got a generic over element type, and it's got functions like map. That's what I mean. We used the map function before, and it has a somehow reasonable type. It's parametric over the elements and the result array type, and it gets a function from the element type to the result element type, and then produces a new array with the result type. There's some throw stuff in there because the Swift compiler is not only picky about mutation, but also about exceptions. So exceptions are statically tracked too. So you see, Swift statically tracking is about as kind of tied up as Haskell or something. Okay, so this is map. And here we have something which you can use to implement shuffle. It's a swap function. You give it two indices, swaps it around. And what you see, the signature of the function says it's a mutating function. That's for all functions. You cannot define a function in a struct that does any mutation without giving it, telling that in the type signature. So it's a little bit like having to declare I/O for I/O function in Haskell. And that means the compiler knows exactly which functions are mutating and which are not. So now we got a chance to implement our cow. So we use a box again. Payload gets into the box. Something like map is like a getter. We just forward to the map function of the box, and the result, return the result. And then for swap add, well, we can use the exact same trick as before, because we now we are about to mutate. So we use the same conditional to check, is there more than one reference? If so, produce a copy, and then mutate after that, mutate the copy. And then we're done. So it's a very similar setup as with the setter getter, only that it's actually at the functions and not at the properties and the setters and getter of the properties. So this is only possible because Swift has such strict mutability control, and we know there are no other mutating functions. It's impossible because the compiler won't allow them. Otherwise, this wouldn't work. So it pays off that Swift is so totally picky about mutation. But let's get back to this, memory management. So Swift, I mentioned it in the beginning, it really cares about resource use and in space and time. And it also cares a lot about the allocation latency. And you may wonder, Now, actually, I don't know how many of you know, at the time when Swift was already internally developed at Apple, 2 versions of macOS actually shipped with the tracing garbage collector. Did you know that? But then they stopped it. And one reason was, like on the iPhones at the time, you know, they were very memory constrained devices because memory used to suck a lot of energy and battery life is super important. So very space constrained, but with a high resolution screen. So images, high resolution images for the high resolution screen were kind of problematic in this tight memory environment. And if you kind of scroll through a scroll list with images, there's a lot of loading images from memory immediately when they're off the screen, getting rid of them again happening. Otherwise, the device would run out of memory and you get out of memory exception. Process is killed, doesn't look good. And the problem with the tracing garbage collector is there's a pause, a time between the object is no longer referenced until next collection. And that's called the deallocation latency. With reference counting, there's no such thing. This was one of the main reasons they stopped this experiment. The other thing is stop the world pauses. That's what people usually talk about. Like it takes a while for garbage collection to do its job. And you may think, do I care in my server software? But there's not only server software. So there's another talk I want to recommend to you from Miguel de Icaza, the guy who did the GNOME desktop, the guy who did Mono, so the C# for non-Microsoft platforms. So he's got he's quite famous, I think. And he is now doing Godot. Godot is an open source kind of framework like Unity for doing games and 3D stuff. And Godot used to use C#, and with his company, they try to kind of get the C# use kind of around this problem. So even with the resources of Microsoft, to implement garbage collection for C#, still this is a problem in games. And so now he's using Swift because no problem anymore. Another thing about resource use. So this is called automatic reference counting in Swift. It's automatic because in Objective-C you had to do it manually. But now there are also kind of non-copyable types. So there's kind of ownership tracing, Rust-like kind of stuff. And embedded Swift. Embedded Swift is part of the main compiler. It's just a flag. And there's an interesting blog post for this Playdate, this like very resource-constrained device. And they kind of re-implemented some of the example programs which are originally in C. And the size of the binary produced by Swift compiler is even smaller than what the C compiler produces. So not bad. All right. To summarize, Swift makes this distinction between value types and reference types. And that pays off big time because it also tracks mutability very careful. And as a result, we can implement copy and write bulk value types efficiently. This is done throughout all of the standard libraries in Swift, but you can write your own quite easily as well. And that's really a kind of usability and performance sweet spot, I would say. And finally, well, I mentioned I'm writing this new app. Actually, I'm kind of getting to early beta testing. So if you want to test a new Haskell Acta IDE, let me know. Thank you very much.
Thank you very much, Manuel. I think you are here all still for questions. And there's the first one.
Yeah. Yes, it's funny how history is repeating. Are you still familiar with the extinct language Opal?
Opal, yeah, of course I'm familiar with Opal. I did my PhD at the TU here, and Stefan Jenichen sat next to.
Yeah. So I did as well. Just some remark for people who don't know. Opal was developed a short walk from me, and it had copy and write optimization based on reference counting 30 years ago.
Yeah, it also used reference counting, that's right. Yeah, because it's strict language. Yeah, but
Yes.
yeah, so I mean, I didn't go much into history. So, for example, early versions of C++ also made it easier to have copy and write for bulk types, but they don't have this distinction with value types and so on. So it was still messy, and they chucked it out at some point. Yes.
How do I know for the built-in types? Is it documented? If I understood correctly, for array and map, they use copy on write in the system, so I don't have to implement this myself. So what you told, for about half of your talk, I thought this was by default in Swift, and I always wonder, okay, where's the cutoff for structs? From how many fields does it do this? And I realized only later, for structs, for things you implement yourself, you must decide when to use copy and on write, and if it's the right thing for your application. And where's the cutoff point in data type size is probably depending on how often you mutate or not.
Yeah, that's exactly right. So the Rick van Voorten in his talk has some benchmarks. So he benchmarked kind of its mini application used by Apple in a lot of example programs, and he used his library with the macros on that, and so that's a struct which is not super big, but he already got memory and runtime improvement out of that. So at the end of the day, it also depends on the usage patterns. But so once you have a few properties in a struct and it's copied a lot, then it might already pay off. For collections, because they can grow arbitrarily big, I mean, I think it's always a good idea. And all the standard collections, also libraries which are not part of the standard libraries, but just on the package manager, for collection types, they are all, as far as I know, using the pattern. So it's very, I think for a production-ready collection library, people expect that we do that. You were already...
I'm still confused. Why doesn't the compiler implement it? Why isn't it built on the compiler? Why I implement it as a developer?
Well, for vector, I mean, it wouldn't make sense. It's too much overhead. So in fact, the compiler actually does a lot of preventing copying. So there is LLVM. It's all based on LLVM. LLVM has a very sophisticated kind of analysis to remove copies of value types and minimize actually a reference counting overhead, so the decrement of reference counting. So this is a huge story in LLVM. But whether for your struct it makes sense or not, that really, I mean, it often makes sense, but not always. So for a compiler, it's a tricky thing to do automatically because sometimes you will make the program worse. That's the reason.
Yeah, what bothers me a little bit is that the type is not enough to tell you what you can do to your variable, because it matters if it's left bound or lower bound, right? So what's the rationale behind that? I mean, I would prefer if I see the type that now I know what I can do. Yeah, but now if you have a variable type vector, you have to find the binding. Is it left bound or is it lower bound? Now I can updated or?
Yeah. So as a Haskell programmer, this was my first reaction too. So I was kind of like, oh, it should be type. But, well, I'm just saying this is a Haskell programmer's gut feeling. I don't know whether you use Haskell, sorry. For many Haskell programmers, it would be the natural reaction. But I have to say it's actually quite a balanced system because it distinguishes between having value semantics and reference semantics, that's in the type, and between being mutable or immutable, that's in the declaration. And very often for, let's say, if you program in a function style in Swift, then you typically will be using mutation only very locally, right? You get lots of stuff into your function, and then you say, okay, this array I want to update in a for loop because I'm doing lots of updates and it's random and it's very hard to optimize otherwise. So I bind it, var bind it, and then I do that. And then I return it, and I know no caller will ever notice anything about that. And that boundary, that kind of purity at function boundaries, in my experience, is much more important. And locally, you're close to the declaration anyway, so you know what's right and what's left. So just saying, in practice, actually, I've been a lot happier with it than I thought I would be when I first read about it.
If you don't do the copy in the property setup, do you get structs with reference semantics? Or did I miss something?
Well, you can of course put class references inside structs, and then the struct is as value semantics, but everything you reference, which is declared as a class, is reference semantics.
So it's not enforced.
So it does. It's not enforced that structs can only contain structs. Structs can contain everything. Classes can